Hello everyone, this is episode 3 of Advent of Code. In this one we'll be doing exercises from day 6 through 9. And this is it. Let's just get to it. So we're starting on day 6. As input we would receive a sequence of numbers separated by commas. And these numbers correspond to fish. Every number would be one fish. The number, what it really says is how many days till the fish replicates. Currently we have 3, 4, 3, 1, 2. On the next day we would have 2, 3, 2, 0, 1. And when we have a 0, on the next day that would change to a 6 and then 8. So basically, when a fish replicates, it will create a new one with an internal timer of 8, but it itself will go to 6. So when the new fish goes from 8 to 0 in 8 days, it will also split into a new one with 8, and the old fish will keep the number 6. So here we have some visualization of how it transitions. And based on that, we had some input, which was also a sequence of numbers, just like the example. We would need to calculate how many fish we would have in total after some amount of days. So in the first part of the task, this would be 80, and the numbers would be still kind of reasonable, like thousands. In my case, it would be 300,000, but that's not a really huge number when it comes to computing. But in the second part, we would need to do 256 rounds. And at this point, it was starting to get tricky. So for this task, I started with a naive solution. I just folded over a sequence of the rounds. And for every round, I would basically take a list. Like I would start with what I parsed from the input. But for every fish in the input, or in the current state, I would flat map that fish to the next fish after the round. So it would be either the same fish with the number decreased or two fish, 6 and 8. So basically by folding on the rounds, we ensured that we start with this initial state. And then after we do a round, we will pass the result of that round to the next round. You could do the same with just manual recursion or something like tailrec-m, and like in the previous video, but here I just went with a fold. So this solution was sufficient for the first part. I did 80 rounds just fine, very quickly. But when I run this with my, like even the test input in the second part of the task, then things started to get tricky. So my worksheet didn't even complete. So I thought it was like hanging. It was, well, it was not. It was still busy doing work, but I decided to make it a full-blown Scala file at that point. Then I added some print lines to see how many rounds I was doing, and I noticed that it was just slowing down. Like the more rounds we did, the slower each round would take to calculate. And in this naive solution, I would only get to like round 140, but this was nowhere near 256, and we were already going so slow that, as far as I know, it would take ages. And what I've heard from others is that it will also blow my memory, because I don't have this much memory to fit all this fish into it. So I spent a good chunk of work on some futile attempts to do this in a smarter way. I'm not going to explain all of them because it's just borderline boring and wrong and just a waste of your time. But I'll say this, I was looking for some sort of formula to calculate this, like maybe even in constant time, but I didn't come up with anything like that. Any kind of pattern that I would see in the results of these rounds? Well, I didn't really see one, so I couldn't really abstract it away. So I was thinking of like skipping some rounds so that, for example, if I had 200 rounds more, but my fish was like 6, I could subtract 6 from my rounds and just jump straight to this point of replication. I didn't really complete that approach because I just thought it wouldn't really work. Like it would probably have optimized a bit of the time, but just in like a linear fashion, and I needed something more scalable because this was an exponential algorithm and, well, an exponential problem that maybe could have been solved in a more optimal way, but this wasn't really helping. Not only that, it was also much more complex, and at some point I just didn't understand what I had written a minute before. I had an idea for like a cache, so to see how the lifetime of a single fish would change during like 8 or 9 rounds. And although I didn't really finish that solution either, I think it put me on the right direction to do some kind of memorization. So I realized that there was actually some duplication in this problem. I was actually doing the same calculations twice by recursing through the same kind of numbers over and over again. So I decided to do some sort of memorization here So I created a memory map, starting with a mutable map just to make it easier to share it with all the calls to this function. Then I took my original implementation and I basically factored out the fold left and made it an actual recursive call. And instead of a flat map, I would have basically 2 recursive calls, like one for every new fish, like the 6 and then the 8. And every time I was about to return from this function, I would also put the result into that map. So then if I get the same input again, I would check first if I have that input in the map, and if I did, I would just take that instead of doing any kind of more computations or recursion. And this was really fast. I just got the right result for the example, and then I run this with my real input, and I just submitted it and it worked. So for the refactor, I didn't really do much. First thing I did was extract some code so that I could run the same thing with my test input and my real input, and also do some assertions that we defined in the previous videos library. And then I replaced this mutable map with a state monad in which I would have this sort of memory for the already computed calculations. And eventually I replaced this explicit state monad and its operations with a stateful type class from catsmtl, and just used that to do my state changes. Later I added some stats to see how many cache hits I was getting, and for the first part it was 34%, and for the second part it was only 19%. So this doesn't seem huge because I was just getting a value from the cache in like every 5th case. But when you consider that some of these would have been very expensive to calculate, then this actually makes sense. And it's, it doesn't really matter because I'm still solving this task in just like a second or even less, instead of doing it forever. An alternative implementation that I could have used, something way smarter than what I did actually, was to realize that the numbers that were in the input and like throughout the whole duration of this application, we would only deal with numbers of like 0 to 8. So no matter how many numbers in a round we would get, they would always be just, groups of some amounts of these numbers. So we would only actually need to calculate the things like 9 times. So recurse 256 times for 9 specific inputs. And basically we could group all these items at every stage into these groups, just group them by the number and put the quantities in there, then compute the result and multiply it by the number of these numbers. And it's all simply because if we have 2 identical fish on the same stage, they're going to end up having the same kind of families, and all we need is actually just the amount of their family tree. We don't even need the whole list or the whole tree, we just need the number. So the whole problem basically becomes linear, like we only need to loop n times for n rounds. We still have a potentially very, very long input, and we have to group it, which is not really optimal, but that also can be split into like multiple threads or whatnot, so there's plenty of room for optimization here, just using this one principle of grouping the inputs. Obviously I didn't realize this by myself, so thanks to my friend Camille for his solution for this problem. So after a quite challenging day 6, we have day 7, which was actually a breeze. This is one of the rare cases when I actually get to sleep through the beginning of the task. So at 6 AM when it launched, I was still in my bed. I was actually, resting like a normal human being, which is funny because this task was much easier than most of these tasks which I had done at night, or at least started at night. Anyway, in this task, we also got a sequence of numbers in the input, and also separated by commas. And these inputs were positions of crabs on a horizontal axis. So basically, you line up a bunch of crabs along a line, and the problem was to find the spot, like on the line, that when you sum up all the paths from every crab to that point, it's the shortest. So like the optimal path to a common meeting point. These must have been some like mechanical crabs because they run on fuel. So for every step that a crab makes, it costs 1 fuel. So there were many ways to find the solution here. I went with the brute force one. So I basically found all the possible positions between the lowest position of the crabs and the highest one. And for every one of these points, I would actually compute the distance to that point from all the crabs, and I would sum it. And then I would take the smallest number out of the result. And it turns out that it was sufficient for the first part. So part 2 was pretty close to part 1. There was just one complication. Instead of each move costing 1 fuel, we would basically have moves that get more expensive as you go. So the first move would be 1 fuel, the second move would be 2 fuel, and so on. So in this case, the cost, like the total cost to travel like n steps would be the sum of all integers between 1 and n. So that is the arithmetic progression. And there is actually a formula to calculate the sum of such a sequence, which is you multiply n by the sum of the smallest and largest number and divide the whole result by 2. This is also built into Scala's range type, which is what I used. I just changed the way that I did distance calculation to that, and it just worked. And the refactor this day was really simple. Like this time I just wrapped the whole thing in an object, and I extracted a function to like solve a generic input, and with a generic cost function, the cost function taking an int and returning another int. I added some assertions, and that was it for the day. Now day 8 is something. So I looked at that task. I was actually waiting at 6 a.m. to see the task again because I was still up, just to give you some background here. And I saw like the first lines of input. I was like, oh, this is interesting. This must be really just an overcomplicated way to say what they want to say. But then I noticed how long the page was, and it was like 4 pages of scrolling for just step 1. So I just decided, nope, and I'm going to sleep, and I did. And I actually implemented this only at like 3 a.m. the next day. So I hope you understand how difficult it is to explain this in a short, concise way. So here we're supposedly dealing with like 7-segment displays. So this kind of displays for digits, like you would have on a night alarm clock or something like that, or maybe in a bus. And every digit has a specific way to show it, like you would only highlight some of the segments. So in this task, they numbered the segments. Actually, they gave them names. So like A, B, C, D, E, F, G. And for example, all of them would be just 8 and C, F would be 1. And our input in this task was a bunch of lines, and every line would be just some words using these letters, and then like a vertical bar, and after that bar, some more words also using these letters. And you're thinking, oh, that's easy. You just have to decode some of this using these patterns. Well, that's not really what you had to do. The main complexity of the problem here is that we do have to calculate like the number made from the digits on the right hand side of the vertical bar, but the encoding of all these numbers is not as it was defined in the first place. Like it's not actually CF that corresponds to 1, or we don't really know if it is. And every line can have a different encoding, but within a line, the encoding would be consistent. So for example, DAB in a single line would always correspond to the same digit, and it would always be 7, because only 7 has like 3 segments. Anyway, long story short, we would need to basically crack all the possible encodings, so ways that you could write down a number on a 7-segment display, and find the right ones that were matching every word in the line. So for part 1, we got a really good hint that some of these numbers, like some digits, actually have a very unique amount of segments that they use. So 1, 4, 7, and 8 had unique segment counts. Because 1 only had 2 segments, 8 had all the segments, 7 had 3, and 4 had 4. So in part 1, we were supposed to find out how many 1s, 4s, 7, and 8s we had on the right hand side of every vertical bar. However, I just thought it would be a good idea to just completely decode everything and just be able to decode any number in the output. And it was actually already possible. We would just start with these numbers to find the right encoding. I didn't record the whole implementation that it took me because I did it in like 17 minutes, by far the longest of all these tasks this year. But after I tell you about the second part, I'll just tell you what I did. So in the second part, we're just supposed to actually decode all the numbers, the whole, like all the digits on the right hand side of the vertical bars, and sum them up together. I mean, sum up all the numbers. Like we got some digits, you would have to make an actual number out of these digits, and you would sum up these numbers, not just the digits. So this was really a lot of fun to implement. I decided to call every word a pattern, and the pattern would always have a numeric value. This value would use up to 7 bits, so I could have used a shorter numeric type, but I used int. And the encoding was basically like right to left, A to G. So every binary digit from right to left would correspond to the increasing alphabetic characters. So for example, if this was 4, then the pattern would be just C. If this was 5, the pattern would be AC. And because it doesn't really matter if there's a CF or FC, this actually worked really well because these were the same value, the same integer. Although the input didn't really have any duplicates, so that didn't really matter that much. So every letter had like a mask, which was at most 7 bits. I created this by taking a 1 and shifting it by the appropriate amount of bits. And then to check if a pattern has a specific digit, I would pass the mask of that digit and basically do a bitwise AND on the value and the mask and check if the result is the mask itself. Because if like there's anything in common and it's the same thing as the mask, then it just means that the number had the mask. The idea was that if I could get all the possible ways to encode these numbers, I could take that and slowly chip away and just reduce this to a single encoding that works for a specific line. So for every line, I would just do some fun sorting to start with the unique numbers, like 1, 4, 7, and 8, and I would put them in front of the new list. At the end, I would put everything else from the examples and the targets. The examples being the things on the left side of the vertical bar and the targets being the things on the right-hand side of the bar. And I would fold left on that to start with the initial possibilities for the encodings and try to minimize them. So what minimization actually did, we would take a set of encodings, a set because these were just maps, and we would only keep the ones that still leave a possibly valid digit when we decode the pattern using that encoding. So I actually split the decoding with the encoding part into two things. First, we had the transcoding, which is basically going from one pattern to another one using an encoding, and then decoding that, which was basically just a lookup to take the digit that is encoded using this exact pattern. So for example, if our pattern was AG and the encoding was it included something like A is C and G is F, then we would actually try CF. And we would do a lookup on the map of patterns and digits. This is of course not the ideal example because CF is already unique. We already know that it's a 1 because there's 2 segments, but you get the idea. So I would just transcode all the patterns with the remaining encodings and move on to the next pattern within that line. And at the end of it, after all the fold left, this had to have a size of 1. The remaining encodings, there should only be 1 at this point. So I added a require to just make sure that it's true. And I just extracted the head of that set. And this whole thing was the crack method, which was giving me the encoding of a line. So for every line of the input, I would crack it, get the encoding, take all the numbers in the target, transcode them using that encoding, and just decode them to the digits. This would give me a list of digit, every nested list being the digits on the right-hand side of a vertical line in a single line. But that was actually part 2, summing all the numbers here. So for part 1, we would actually flatten all these lists into a single long list of the digits, and we would count how many of these digits were actually 1s, 4s, 7s, or 8s. And we would just print that. That was my result for part 1. It was correct. I think it was correct the first time. And I just submitted that, it worked. So then part 2, everything stayed the same, except as I said before, we would need to basically find the full numbers on the right hand side of the vertical pipe and sum them together. So given these lists of lists, we would convert each such nested group to an actual integer and sum that. And for the conversion, I would normally suggest that you just take the integers and concatenate them as strings and then parse that to an integer or long. But here I want it to be fancy, so I just zipped the numbers with indices in the reverse, and I just basically multiplied by the right parse of 10 to get the right number. And I actually used longs here. I suspected that the numbers would be really huge, and they were. So this was a good call. I just happened to make it at the right moment and not when I was actually trying to guess the solution. In the process of the refactoring, I didn't really do anything fancy. So the only things that I really did was separate out the code that depended on the input. And given that I wasn't really in a hurry when I was doing it the first time, it was already quite close to that. So I only had to modify a couple of lines. Then I made the whole thing a normal Scala app instead of a script in a worksheet. And I added some comments to state what every group of functions was doing. So for example, I had a parsing group, which basically did parsing of the lines or of the patterns. Then I would have a group with like the data, which was the mappings of digits to these masks in ints, and the patterns of every specific digit, like which segments it would have. So basically a pattern value of every digit. And finally, like the whole logic that solved the problem. Now it's time for day 9. In this one, we got a 2-dimensional matrix of numbers, and these numbers were just digits from 0 to 9. And basically we were supposed to find the numbers that had no neighbors that were smaller than them. And by neighbors here, we only counted the ones on top, on bottom, on the left, on the right, but not like diagonals. And these numbers that didn't have a smaller sibling were called the low points. There was also something called the risk level, and this was basically the value of a low point plus 1. And the first task of the day was just to sum all the risk levels of all the low points. So I did this in a slightly inefficient way because I made a map, and you would probably do much better to do just 2 nested arrays to have constant lookup, arrays of vectors. I went with a map. So basically for every index of a character and a line in the input, I made an entry in the map. So like by the coordinates in the input, you would be able to find a value. Then I tried to count how many points in this map had no smaller siblings. I accidentally implemented siblings in a way that actually included the diagonals. So that took me some time to notice, but otherwise it was relatively simple. We would just like find all the differences between the position of the point that we're looking at and a possible position of a sibling. I would look up all the matching things in the map if they existed, because they didn't have to, like we could have been on the edge. So I just looked up the appropriate ones and tried to find all of them and the smallest one. And then I would check if my number is still smaller than the smallest one out of these siblings. This is the best part. I didn't actually add the divs to my point. I was just always looking up these 4 numbers, these 4 positions on the whole map, and never actually looking for the actual neighbors of my point. Then I noticed my mistake. I fixed it so that only like these top, bottom, left, right values would be included. So having fixed all these issues, I used my real input and I got the right result. Now in part 2, let me just give you more context for the task. So basically these numbers that we had, the values were heights of like waterfalls or like pools, and in here they were called bassins. So every low point that we already found in the first part would be like a place that all the water from a particular basin would fall to. And every low point would be part of exactly one basin. So like all the water in the basin would flow to the low point by the horizontal and vertical lines. The diagonals was still not included. And the expected result was basically the product of the sizes of the largest 3 basins. Largest by the amount of unique positions within them. And here I actually had the right idea in the first place, but then I didn't, I made a small mistake that kind of messed up the rest of it, and I just had to try it much later in the day. Oh, and also quite importantly, every point in the input except the points with the value 9 would be part of exactly one basin, and the 9s wouldn't be part of any of the basins. So the idea was that for every low point, I would basically find its whole basin. So find basin would take the position that we're currently at and the current level of the water, and we would basically find all the siblings of the current position where the level was the current level plus 1. And I now know this, but this was not the right way to do it. However, it worked with the example, so this confused me for quite a while. Anyway, if the current level was 8, then I would just return the current position because nothing else could ever join my basin, because that would have to be a 9. At this point, I had to make a change to my siblings function to find not just the positions, but also the values at them. This would make it much easier to implement the second part, because I needed this value, this height, in order to filter the siblings by the right number. And then I also needed the position so that I would know where to recurse, because I would take that position and then look for, siblings of that, and so on and so on. So I would just call find basin with the new parameters, like of every next sibling, and basically grow the whole basin this way. Initially, I wanted the whole function to return like an int, the amount of items in the basin, positions in the basin, but then I realized that it would have been more difficult to like deduplicate items this way. So I changed this into a set of positions, and then the deduplication of a set happens automatically, so I didn't have to worry about that at all. So I would just put the whole positions into that set, returning the current position if there are no siblings, and if there are more siblings, I would add this current position to the set that would be returned by the recursive call. So maybe you'll notice that this recursive function here is not stack safe, like there's no tail recursion, but at the same time the inputs are going to be digits. So the highest input that I'll get is a 9, but I'll never actually get to a 9 because I'll stop at 8. So this actually will never go that deep because I'm guaranteed to get like the next increased level. So I'll never actually just jump to a random super high number, or I'll never do any negative numbers either. So this should complete in a reasonable amount of stack frames. I got rid of the checking for the level 8 because at that point the code basically behaved the same way as previously, but this was giving me the wrong results again because I was no longer ignoring the 9s. So I added an explicit if to check if there's a 9. If the current level was 9, I would just return an empty set. So having added that, I was able to find the largest numbers by sorting the list of these numbers and doing a take right 3. This isn't optimal because you actually need to sort the whole list, and sorting isn't a linear problem. You can do this in a linear fashion. You can even do so with a monoid. I encourage you to try to do it. Maybe we'll discuss this in the comments. If you're curious, let me know. Anyway, I used my real input, and the result was actually wrong. Like the website didn't accept that, even though the result was okay for the example. So I tried for a while here looking for potential bugs in my code, and there obviously were bugs, but it wasn't clear what they were because the example input was still working well. When I was thinking about this during the day, I was thinking like the website didn't actually specify that going down by the water levels meant going down by exactly 1 point, like 1 level. So maybe I could have changed this operator like is equal to level plus 1 to is more than the previous level. So that was one of the contributing causes to the issue. But then when I fixed that, there was still something like a leftover, because for the next iteration, I was still using level plus 1, whereas I should have used just the level of the position that I found in the siblings. But it only came to me after a while of debugging. So here's what I did to get some help here. I made a small visualization. First, I wanted to see if there were any numbers that were not part of any basin and that were not 9s. So I basically took the input and marked every point, like I actually wrote this in red if it was not part of any of the basins. So then I replaced the 9s with white space, and then it was clear that these numbers should have been part of these basins. Like I could actually see them, so I could actually see every basin on this input. I even tried displaying like the low points specifically in a different color to understand maybe I was missing like some of them, but no, I was actually getting one in every one of these clusters. Later on, I wanted to actually separate out these basins like in a visual way to have colors. So I did the best effort of separating them out by using a separate color for every 6th basin, because I didn't even have enough colors in the terminal to use, so I just used these 6 that I knew, but I still didn't see what was wrong. So then I did something that actually showed me the way. Instead of showing the values where they were, I would show like the identifier of every pool, every basin. But because I only had one character for each one of them and I had a lot of these basins, I could only show 1 digit. Now I realize I could have actually used letters for this, but I ended up using just the last digit of the number of the current basin. So this showed me that there were just groups of these values together, like just next to each other, which were considered separate basins, but they couldn't have been, because a basin would always end at like a 9. Like in the middle of the board, you cannot just end at a 6 when there's a perfectly normal number next to it. So I went back to look at the recursive function and I noticed that I was actually not using the level of the next point. So I changed this, I updated all the code, made sure to check like for larger than the current level, and I tried the test input. It was right again, and also my real input was giving me a different number from what we've seen before, so I tried that and it was correct. So I'll just let you look at this visualization for a minute, and let's move on to the refactoring. So eventually most things here ended up being methods or lazy vals on the points data type. And also the points data type was even used for the low points value. So that also was just another instance of the same class, which is sort of the reason why I had to do lazy vals, for example, for low points, because otherwise there could have been like an infinite recursion trying to calculate the low points of the low points of the low points and so on. All that remained was adding some assertions for the test input, the real input, and I was done. Thank you for watching. I hope you enjoyed this. If you liked the episode, leave a like, subscribe, and I'll see you in the next episode.